Hey, welcome. Today, we're diving into the invisible rules that basically run everything. I'm talking about your car engine, your phone battery, even the sun itself. It all boils down to one powerful science, thermodynamics. This is the story as energy, and we're about to see how it connects, well, everything. So let's jump right in.
So let me start with a question for you. What could a massive, sprawling power plant possibly have in common with you making a cup of tea in the morning? It sounds kind of crazy, right? But the answer is everything. Seriously, they are both playing by the exact same set of rules about energy, heat, and change. And our whole goal here is to connect that huge industrial scale to something we all do every day.
All right, to build that bridge between a power plant and a tea kettle, we first need to get on the same page with the language of energy. So, in this first part, we're going to lay down the vocabulary. What do terms like energy, heat, and work really mean in the world of thermodynamics? You've probably heard of mechanics, right? That's the science of how things move. It's all about forces and speed and things bumping into each other. But thermodynamics asks a much deeper question. Why do they move in the first place? It's the science of the energy that drives the action, how it moves around, and how it changes from one form to another. So, the main character in this whole story is, of course, energy. And the simplest way to think about it is just the ability to make stuff happen, to cause a change. But here's the absolute number one rule, the big one, the first law of thermodynamics. You can't create it, and you can't destroy it. Energy is conserved. All you can do is shuffle it around and change its form. Now, when we talk about moving energy around, the first thing that probably pops into your head is heat. But in thermodynamics, heat is a very specific thing. It's not something an object has or contains. Nope. Heat is energy on the move, energy in transit, and it always flows from something hot to something colder. It's a process, not a possession. And the other major way energy gets around is through what we call work. This is energy being transferred in an organized, mechanical way. You know, like when hot gas expands in an engine cylinder and pushes a piston up? That push, that force, moving something over a distance, that's work. So here's the bottom line. Heat and work are the two ways energy crosses the line from one place to another. Okay, so to make all these ideas a little less abstract, we're going to run a thought experiment in a very simple laboratory, just a pot of water on a stove. This humble kitchen setup is going to be perfect for seeing all these core concepts in action. Now, in thermodynamics, we have to be super clear about what we're looking at. The thing we care about, in our case, the water, we call that the system. Everything else, the stove, the kitchen, the air, you name it, that's the surroundings. And the thing that separates the two, the pot itself, that's the boundary. So think of that boundary like a bouncer at a club. And depending on what that bouncer lets in or out, we can classify pretty much any system in the universe into one of three types. Let's break it down. First, you've got an open system. That's our pot with no lid. Heat can get in from the stove, and steam, which is mass, can get out. So both energy and mass cross the boundary. Okay, now slap a tight lid on it. Heat can still get in through the bottom of the pot, but the water vapor is trapped inside. That's a closed system. Only energy gets across. And finally, imagine that pot is a perfect thermos, an impossible perfect one. Nothing gets in and nothing gets out. No heat, no mass. That's what we call an isolated system. All right, now that we've got the rules of the game set, let's start our experiment. We're going to follow the incredible journey of our water as we crank up the heat. We're going to tell the story of its transformation from a calm liquid into a really energetic vapor. And believe it or not, this happens in 5 distinct stages. Stage 1, we just have cold water, what an engineer would call a compressed liquid. Then, as we add heat, its temperature rises until it hits the boiling point. Right at that moment, it's a saturated liquid, just on the verge of changing. Stage 3 is the fun part. It becomes a saturated mixture, a bubbling chaos of water and steam. Once that very last droplet of liquid turns into steam, we're at stage 4, saturated vapor. And if you keep adding heat even after that, you get superheated vapor, a really high energy gas that's ready to go do some serious work, like spinning a turbine. Now, that magic temperature where boiling starts, we call that the saturation temperature. We all learned it's 100 degrees Celsius, right? But here's the catch. That's only true at sea level, at one specific atmospheric pressure. If you go climb a mountain, the pressure is lower, and your water will actually boil at a cooler temperature. That link between pressure and boiling point is absolutely crucial in engineering. So, how do engineers keep track of this whole complex journey? They can't just stand around watching a pot boil all day. They need a better tool. And they have one. They use these special kinds of maps called property diagrams to see the entire process at a glance. Because really, any journey, whether you're driving across the country or your water molecule turning into steam, it needs a map. It's the only way to know exactly where you are and where you're headed. And this is what that map looks like for thermodynamics. It's a property diagram. Just look at this path. It perfectly tracks our water's entire trip. We start over on the left as a cold liquid, we move up as it gets hotter, then we hit that flat line in the middle, that's the boiling part, and then we climb up again on the right side as superheated steam. That entire 5-step story we just told, it becomes one single, easy-to-read path on a chart. It's awesome! You might be thinking, hold on, how can a simple 2D map capture all of that? Well, it's thanks to this incredibly powerful rule called the state postulate. And honestly, it's like a cheat code for physics. It basically says that for a substance, like water, you only need to know two independent things about it, like its temperature and its pressure. And from just those two pieces of info, you can calculate everything else about it. Its density, its energy, everything. And that's why a simple 2D map is all you need. Now, if you look at our map, there's this really weird landmark at the very top of that dome shape. It's called the critical point. At this one specific, bizarre combination of temperature and pressure, the difference between liquid water and steam just disappears. They become the exact same thing. If you go past that point, you don't get boiling anymore. The liquid just smoothly and strangely transforms into a gas without any bubbles at all. Okay, so we've spent a lot of time talking about a simple pot of water, but why is this so important? Because that exact same journey, that same map, and those exact same rules are what drive the most important technologies that power our entire world. That's right, the phase change journey happening inside a massive steam power plant, the process that cools a nuclear reactor, even the refrigerant cycling through your air conditioner, they are all just bigger, more complicated versions of our little pot of boiling water. The physics, the principles are exactly the same. They're universal. Now, to actually design these huge, complex systems, engineers have another trick up their sleeve to make life easier. It's a simplified model called the ideal gas. Basically, it pretends that the molecules in a gas are just tiny points that never interact with each other. Of course, no real gas is actually ideal, but for a lot of situations, this simplification is surprisingly accurate, and it makes the ridiculously complex math behind a jet engine something a human can actually solve. And we're going to end with one last really big idea. We know that the quantity of energy in the universe is fixed, it can't be destroyed, but energy also has a quality. The organized, useful, high-quality energy packed into a piece of wood is way more valuable than the disorganized, low-quality waste heat that spreads out when you burn it. This is the heart of the second law of thermodynamics. Every time we use energy, the overall quality of energy in the universe goes down. It gets messier, more spread out, less useful. Which leads us with a huge question. In a world completely dependent on high-quality energy, what does this constant, unstoppable decline in quality mean for our future? That's something to chew on. Thanks for tuning in.